The problems solved so far involved the force causing the object to rotate freely around the pivot. The upcoming problems will examine objects that tend to remain at rest because all of the forces and moments acting on them are balanced, meaning they cancel each other out. These objects are said to be in equilibrium. Engineers are very interested in objects in equilibrium, as solutions to these types of problems allow engineers to further study the sizes and types of materials suitable for the different applications. In this lesson, we will use the fact that in equilibrium, the sum of all moments about any point is equal to 0. The formula is written sigma m equals 0. Sigma is a Greek letter meaning sum of all. Sigma m indicates that all of the moments for the system being evaluated are added together, taking into account the positive or negative sense of each moment. The sum of all the moments equals 0. The seesaw is familiar to most people who have spent time at a playground. Seesaws work very well when two bodies of the same size want to gently go up and down. Two bodies of the same size balance each other, causing the sum of the moments to equal 0. However, when one body is considerably larger than the other, sitting at the end of the seesaw will cause a definitely unbalanced situation. Riders are not able to have an enjoyable seesaw ride when this happens. By moving the larger body closer to the pivot point, this can cause the moments on the two sides to balance each other, bringing the system into a state of equilibrium. The question is, where should the larger body sit? We can use the formula for equilibrium of moments to solve this problem. Body 1 provides a downward force F1 of 25 pounds due to its weight. Body 2 provides a downward force F2 of 40 pounds. F1 is located 4 feet from the pivot point, while F2 is seated at some position closer than 4 feet from the pivot. The formula is sigma m equals 0. Substitute for sigma m all of the moments for the system acting about the pivot. M1 is positive because it is rotating the seesaw in a counterclockwise direction. I check this using the right-hand rule. As I curl my fingers around in the direction of the rotation caused by F1, my thumb is pointing toward me in a positive Z direction. Likewise, M2 is negative as it tends to rotate the seesaw in a clockwise direction. I confirm that my right thumb points away from me when I curl my fingers in the direction of rotation. I can rearrange the terms to read that M1 equals M2. I then substitute the moment formula. M1 is replaced by F1 times D1, and M2 is replaced by F2 times D2. I then substitute the actual numerical values. Substitute 25 pounds for F1, 4 feet for D1, and 40 pounds for F2. D2 remains the unknown for which we are solving. Moment M1 is calculated to be 100 pound-feet. We can then divide both sides by 40 pounds to isolate the D2 term. The 40 pounds in the right numerator cancels the 40 pounds in the right denominator, and the pounds unit in the left numerator cancels the pounds unit in the left denominator. The final calculation, 100 divided by 40 feet, results in D2 equals 2.5 feet. When I get to the end of a solution, I take a step back and see if my results make sense. By doing this, many times I've caught myself with a decimal place error or some other trivial mistake. Does 2.5 feet make sense? Yes, it does, because we initially assumed that the heavier body would be seated closer to the pivot. This problem involves moment calculations applied to a static beam that does not rotate. The beam is perched upon simple supports at both ends, labeled A and B. An object is placed on the beam and labeled C. The object has a weight of 35 pounds, which exerts force Fc on the beam. For this problem, the beam itself is considered massless. The length of the beam, DAB, is 10 feet, and the object is located at distance DAC, which is 3 feet from A. Completing the free body diagram of the beam, replace the simple supports with the reaction forces Ra and Rb. We will use the equilibrium and moment formulas to solve for the unknown reaction forces Ra and Rb. For all moment problems, we get to select the pivot point. By selecting the pivot to be located at one of the unknown forces, we reduce the number of variables in our equation. Let's select the pivot to be at A. The moment of Ra is 0 since Ra acts through the pivot. We can now solve for Rb. The procedure we follow for solving this problem is much like the last problem. After writing the formulas, substitute the known values dAb, Fc, and dAc, and solve the moment on the right side of the equation. Divide each side of the equation by 10 feet to isolate the variable Rb. Cancel out 10 feet on the left side of the equation and the feet units on the right side. The reaction force at B is 10.5 pounds. Does this make sense? I would expect Rb to be sharing the 35 pounds with Ra, and I would also expect it to have less than half the load since the object is closer to A. So yes, this makes sense. In this simple problem, we can see that Ra and Rb acting upward support the 35 pounds acting downward. Since the sum of the forces in the y direction equals 0 in equilibrium, we can now solve for Ra and find that it equals 24.5 pounds. It is common for engineers to calculate the loads on a truss as a first step to determining material types and sizes that will support expected loads. Notice the support on the left is a pinned support, which allows no movement in either the x or y directions. The support on the right is a rolling support, which allows movement in the x direction, but not in the y direction. This is really important, as truss structures, like bridges, undergo expansion and contraction with temperature changes. This truss is loaded with 600 pounds downward at point C, called Fc, and a horizontal force of 500 pounds at point B, called Fb. To complete the free body diagram of the truss, replace the pinned support with reaction forces Rax and Ray, and the rolling support with reaction force Rdy. Now we are ready to apply the equilibrium and moment formulas. Select the pivot to be located at A. This way, 2 of the 5 forces act through the pivot and produce no moment. Add the 3 other moments, noting that MD is a positive moment, while MB and MC are both negative moments. Rearranging the terms eliminates the negative values. We can see the perpendicular distances of the forces at C and at D from the pivot are 24 feet and 32 feet respectively. But what is the perpendicular distance of the force at B from the pivot? I can extend the line of FB back to construct the perpendicular. Notice that the perpendicular distance from the pivot to FB is equal to the length of member CB, so we will call it DCB. Now, for each of the moments, substitute the moment formula, force times distance. Substitute the values for our known quantities, and solve. Isolate Rdy by dividing both sides by 32 feet and canceling units. The result for Rdy is 637.5 pounds. Does the answer make sense? The force up at D is greater than the force down at C. That means the support at D is carrying the entire 600-pound load at C and then some. That extra force is due to the rotation produced by the 500-pound force at B. The force at B is pulling up on the support at A and pushing down on the support at D through the truss members. Evaluating horizontal loads at the tops of structures relates to studying how the force of strong winds affect the design of the base supports of a bridge or building. We have examined moments causing rotation about a point or axis and moments that do not cause rotation but do affect static equilibrium. Finally, we will briefly discuss how moments affect an object that is not constrained in any way, specifically how moments act on an airplane. Aircraft have several features called control surfaces, which are movable flaps located on the wings and tail. These surfaces have the job of controlling moments caused by the force of air on the wings and tail of the airplane. By controlling the moments of these forces, pilots can steer and maneuver aircraft in all directions. The motion caused by these moments, the roll, pitch, and yaw, rotates around three mutually perpendicular axes that meet at the center of gravity. As you can imagine, the interplay of all the forces and moments is quite complex and is a field of study in itself. Moments affect the flight of aircraft by adding rotational components to the straight-ahead translation, providing the ability to dive, bank, roll, and to perform other complex maneuvers. Moments are present in most physical systems, from transportation systems like aircraft, to construction systems like bridges, to biological systems like skeletal structures. Calculating moments and the effect of moments is a key skill in many aspects of mechanical, civil, and bioengineering.